You ready?
I think the levels are good.
Okay.
So I'll have to clarify. In our last talk, we talked about where plutonium and thorium, uranium come from in the first place and why they have so much energy. I was talking about stellar nuclear synthesis, nucleosynthesis. Not all stars can make the heavier elements. Some of them even top out at hydrogen. Like, since it's a quantum event that's happening, some stars burn hydrogen to helium and they have to stop because they're not big enough or hot enough, whereas others will go all the way to supernova.
And was it gravity that does it?
It's gravity and heat,
Yeah.
you know. So you can make a lab on the planet Earth that has enough heat and pressure to fuse things. You know, one of the cute experiments they did was finally turn lead into gold. You know, so it's just a matter of heat and pressure, and then you can get neutrons and protons to fuse into higher, heavier elements. But
Enormous heat and pressure.
Yeah.
Unimaginable.
Unimaginable, yeah. And then so for fusion up until iron is exothermic, and then fission after iron is exothermic. So iron is the low point where if you split it or try to fuse it, you won't get any change in energy. So now the Earth is full of things like thorium and uranium.
That took energy to be put together and therefore are sitting there like a coiled spring.
Yes.
Or like a chemical bond that can be broken to release energy.
Right,
Yeah.
right. Just like a fully charged battery, but the battery is the nucleus.
It's in
There's
the nucleus.
there's energy invested in
Yes.
its structure, and
Yes.
so breaking it apart, you
Really-
can harvest.
Yeah,
You can
harvest.
reap
Yeah.
what the star has sown.
Yes, yeah. The stars going supernova have stored insane amounts of energy into the
Chunks
nuclei.
of metal.
Chunks of metal. I mean, imagine trying to explain to somebody from the past, a gunpowder era, Napoleonic era, like, well, we have even more powerful bombs. Well, what are they made of? Well, it's metal. It's a sphere of metal about this big. And I have some pictures of like plutonium pits or whatever. And if you put them together in the right way, they release so much energy that in an instant they can destroy a city. So here's the size of like a uranium pits. You know, it's
Melon.
a size of a cantaloupe.
Yeah.
Yeah, tortoiseshell.
Yeah. And you wanted to know how you do it. Well, you arrange neutron reflectors and other metals and maybe other pieces of uranium and plutonium in a very precise geometric kind of expanded shell full of explosives just right. And a conventional chemical explosive, TNT, in a second explodes. That's the trigger mechanism, pushes all of these together, and that starts the fission chain reaction where almost instantaneously
Throws them inward.
blasts them inward, increases the pressure. So now a chain reaction of fissions that releases more neutrons. And in a very short period of time, a whole lot of energy.
Theoretically, one atom breaks apart and
Right.
throws neutrons at its neighbors,
Yes,
and
yeah.
It cascades
It
from
cascades from there.
Cascades.
Yeah. And that's what it is.
To the tune of MC squared, apparently.
Right. That's
Yeah.
why.
Yeah.
And so we ended our talk going, well, you can have a sphere of plutonium, and if you release all that energy at once, you can destroy a city, or if you slowly meter it out over time, you can power a city or a civilization for a very long time.
Eons.
Eons. Yeah.
Or
And how you meter that out is the molten salt reactor. That's how you do it. That's where we begin.
so,
The end.
yeah.
So why haven't we read about this in the newspapers? And
It's growing. It's a growing movement.
is it?
The history is that with the Manhattan Project, a whole lot of minds, very smart minds, got together with almost infinite government funding during the Manhattan Project and the few years afterwards. And a lot of experimentation happened, and a lot of people tried a lot of different things. And then after that, it ossified and bureaucratized, into the NRC and the, nuclear IAEA sort of thing where the rules got established of this is what you do, and experimentation has largely stopped. But the story roughly is that a man named, it was like Glenn Seaborg and Alvin Weinberg, who were friends, and like one was a mentor to the other. They were involved in the Manhattan Project. After the war and the bomb, the Air Force wanted a nuclear-powered airplane that could fly indefinitely without needing to be refueled because the ICBM had not been invented yet. So the idea was this airplane is going to basically orbit the planet just in case Russia dropped a bomb on us and wiped out our capabilities. And they built a reactor called the Fireball to help power an airplane, and that was the first molten salt reactor where you...
Did they get it in a plane?
No, they just ran it because eventually the ICBM was built. But the concept was there. That was how it started, believe it or not. And then Alvin...
As another deterrent in the whole MAD scheme,
right.
basically.
And it reached the highest temperature that any nuclear reactor has gotten because the salt is molten and steel melts at like 2,500 degrees. They got it up to like 1,800, 1,700 degrees Celsius. Very hot, and so the basic idea is, and it's counterintuitive, you can dissolve, even the idea that you can melt sodium chloride into a liquid at a very hot temperature is not intuitive. You never see liquid salt, it's always dissolved, you know. So it's not dissolved in water, there's no water in it. And you can melt thorium or uranium or plutonium into it, and just by that action you have built a system that is perfectly that is optimized for heat generation for multiple reasons, and that's the molten salt reactor. And after they built that Fireball reactor, which they didn't generate any electricity or anything with it, they just said, well, it worked.
It got hot.
It got hot. We have a sphere.
How'd they get the salt hot to begin with? Do you have to get the salt hot with...
Yes.
Yeah.
Yeah. You do. You can't sit there and just...
Right.
You can't put solid plutonium next to solid.
right.
Like,
And
go
boo, yeah. That'd be cool.
You just use electricity.
Yeah.
You know, so
Sure.
in a crucible, you melt the salt and then you slowly meter in, probably pulverize like dust and slowly melt the plutonium in. But once it gets going, the plutonium is now molten and suspended in the salt.
Uh-huh.
One of it fissions, releases a ton of heat and some neutrons. It hits another plutonium, and it goes and goes, and you've now started a self-sustaining chain reaction that releases so much heat that it finds a new equilibrium at whatever concentration of plutonium you put in there.
Why isn't it blowing up?
Because it's already molten. It doesn't blow up because it's not a solid metal.
Mm-hmm.
So if you're the plutonium, you're floating and you're surrounded by fluoride or chloride, you know, and sodium. It splits and it releases a neutron, but it can move. It can move through the medium and hit another one. So all that happens is that the salt expands thermally, thermal expansion of the salt.
Right. But, so you say you start it going and then it's hot for a while until it's used up,
Yes,
right?
yeah.
But so is it okay for me to imagine it as just a slower, it's a cascade in the same way where it's this one splits and gets another one to split and gets another one to split. It's a cascade in the same fashion, just a lot slower than the bomb.
Yes and no. It is a cascading chain reaction, but what it has is, because the density is dependent on the heat, the hotter it gets, the salt expands, which decreases the neutron flux.
It's got a feedback mechanism baked into it that keeps it at a regular rate.
It keeps it at it. It finds its own
That's
equilibrium.
so cool.
That is called a negative coefficient of reactivity.
Okay, so it doesn't cascade in the same fashion then.
A bomb or a solid-fueled reactor has a positive coefficient.
It accelerates.
Of reactivity. It's like it's balanced up on the tip. Oh no, it's getting hotter and hotter. That makes it hotter and hotter.
Right, first 1 goes, then 2 go, then 4 go, then 8 go, rather than this thing that just gets the radioactive atoms just get a little farther apart
Yes.
when they're going, and so they find their own equilibrium.
It's self
That's so cool.
dampening.
Yeah.
So a solid fueled reactor, which we have like 400 of them in the world, have positive reactivity coefficients, which means it's like a bomb inside of a pressure cooker. And that's why you have to have all of these computers and people sitting there going, oh no, oh, put in a control rod. Oh
Yeah.
shit, 3 Mile Island, Chernobyl. This is what happened.
Yeah.
You know, it got out of control. With a molten salt reactor, it finds its own balance like a pendulum on the bottom of a rope. You add a little more, it releases a little more heat, and then it finds its new upper temperature, and it just stays there. They built one and they ran it in Oak Ridge, Tennessee, and there was an incident where they were doing tests.
Stirring it.
Yes.
They were skimming it for bugs.
Right. They were doing experiments with it, and it melted a piece of metal and it dropped in some radioactive elements into the salt, unplanned, unaccounted for, and they're like, "Oh no, what's going to happen?" And the reactor went, whoop, and it got a little more reactive, and then just leveled out.
New equilibrium.
New equilibrium.
Huh.
It is walk away safe.
Now, this is it comes back to how did people figure this out? Theory led the engineers to do this. I mean, it was theory.
Yes.
These two theoreticians.
Yes
Why
and no,
not?
because plutonium went from being unmade into being they understood it in like 3 years because there was so much government money behind. There was a lot of tinkering.
Oh, okay.
That-
so the
that-
engineers were involved too.
Oh, of course.
But I mean, so it wasn't designed out of the theoretician's
No,
mind.
no.
They had to go in and tinker.
It wasn't the benzene ring dreamed up.
No,
and,
you could say that Einstein was the theory, and then after this, they're sitting there dinking around because there's so many isotopes.
Yeah.
There's so many variations. It's really difficult. There's uranium-238, 235, and 234.
Yeah.
You know, there's and all these other isotopes, and then the fission products. And there's things that happen because fission is going on. There's a lot going on. It's like you have to mess with it. It was Edisonian and theoretical.
Okay.
You know?
Interesting.
Yeah. What that means also with the negative temperature, the negative coefficient of reactivity, it allows the reactor to load follow because it doesn't work just in one direction. It works in the other one. So if this fission reaction is going and it's found its equilibrium, happily going along, the reactivity of the plutonium, the chain reaction, fission reaction, is happily matched its density and heat. Now I put a heat exchanger on there because I want to make some steam.
Sure. You want to harvest some of that heat.
I'm cooling the salt down.
Yeah.
It gets more dense.
Right.
It's like pushing on it.
I got you.
Yeah.
I got you.
And so it matches it. And so
Right.
you go, there's a big blizzard coming in the eastern United States. And
We're going to need to draw some more.
We're going to need to draw some more. The electric grid is going to double its use because everybody's turning on their heaters. Right? And since we are such an enlightened people, and we replaced all our coal-fired plants and natural gas plants and hydroelectric dams with these molten salt reactors in the year 2031, go ahead. Crank up the fucking heat. The reactors can handle it. They just go whoop and they match it. It load follows, which is exactly what you need for the electric grid.
Okay.
You don't have to go, oh no, we need to truck in more coal.
Okay. Now, here's a political question.
Yeah.
One is the reason this wasn't continued to develop was because of pressure from coal and oil, or might that have been a motive to?
Yeah.
Right. I mean, you mentioned the ossification and
Bureaucratization, yeah.
Right. Of the post Manhattan experiment, this nice period of almost unlimited resources and lots of brilliance sitting around together and plenty of experimentation, and then later sort of now there are these just a few tracks that are appropriate to pursue. So I was wondering the same thing. Does capital have anything to do with who decides which are the good tracks you can follow or not?
Sure.
Well, the villain in the story, apparently, the story that I've read about this, the villain is Richard Nixon.
Oh, he's an easy one.
He's so easy.
Oh my gosh. As if we needed another reason.
There were two main tracks. One was the molten salt reactor, led by Alvin Weinberg at Oak Ridge, Tennessee, where he was in control of the program, and he was like 33.
He was a great physicist.
Oh,
I mean,
he
I
was.
just read about him in other contexts.
Yeah,
Not in this context.
Yeah,
Wow.
he knew his stuff.
I only know like 3 physicists.
No.
Yeah. And he also held the patent for the light water reactor, or multiple patents for it, which is what we have today. But that path went towards California, and Nixon, for political favors, pushed that. Political considerations said jobs and federal money is going to go to the light water reactor in California, not the liquid.
But why? Okay, but yeah. So what? What made it more?
Another reason was
Why was it in his best sell? What, couldn't he have sold the same thing but with the thing that was bad? I mean, couldn't he have acted in his own self-interest and used the same messaging and made it
So he probably wouldn't
the
have
molten
understood.
salt reactor
Yeah.
instead? Like,
he openly said he didn't understand.
Yeah.
Being self-deprecating. Oh, I don't understand this science. It was never my forte anyway. There, I could show you the speech he's giving, but it was. It's distressing to read about these missed opportunities, because they built that molten salt reactor and ran it for 4 years in Tennessee. No incidents or problems.
right.
From 1965 until 1970.
Yeah.
It ran for what, 22,000 hours?
It sometimes makes me imagine. It's sort of like retrofuturism, or something. That's not the wrong word for it, but I imagine a future and then imagine that the people in that future looking back. Right,
Yeah.
Like is wine? You know, is this going to be a saint of the
I would
of
put a
some
picture of him on my wall.
hypothetical,
Yeah,
utopian or at least better or
Yeah.
more sustainable or less cruel future, And here's this guy who,
Yeah.
or some collection of guys who advocated for this thing.
Yeah.
But 7 decades, 8 decades,
Yeah.
10 decades before it ever was made manifest.
Yeah.
I mean, electricity had a transformative effect. You would have there's Saint Tesla and Saint Maxwell, right? Well, Saint Weinberg is the one who put the power behind the electricity. So the current solid fueled reactors we have, they're almost all of them are called the light water reactor. And this is the type of reactor that people go to school for to become a nuclear engineer. Like, your path is known. It's like this. It's like running an airplane.
Right,
This is what you're
right.
trained to do.
Or a locomotive engineer or something.
Yeah.
Yeah.
Every T is crossed, every I is dotted, every bolt is accounted for.
Yeah.
So you find it's fueled by uranium, and specifically uranium-235, which is less abundant than silver in the Earth's crust. And you find a uranium body, and you mine it, and you turn it into yellow cake, and less than 1% of that yellow cake is the uranium-235 you need. 99.3% is uranium-238. You have to enrich the uranium-235. This is what they talk about when there's nuclear proliferation. If I had a suitcase full of plutonium or uranium-235, you could make a bomb out of it. It's getting it to be enriched. That's what's important.
Mm-hmm.
You enrich
So
this.
the isotope is
Very important.
Yeah.
right.
Uranium-238 has a half-life.
Just the number of neutrons
Yes, yeah.
in the nuclei of these atoms.
Yes, chemically it's the same.
Right. Right. It reacts. It follows all the laws of chemistry the
Yeah.
same.
Yeah.
Because chemistry is electrons and
Electrons.
polarity and
The periodic table.
And that's
Right,
why,
right.
And that's why that's why enrichment is so fucking expensive and difficult. You're trying to separate two things that have a difference of weight of 3 neutrons. How do you do that? We paid ants to go
Holy
and lift
crap.
a grain. No, that you can't. Yeah,
And this is centrifuges?
that's the centrifuge.
Yeah.
This is
that's such a funny thing. Because a centrifuge is such a clunky, old, mechanical,
Yeah.
just brute force sort of idea, right? We'll spin it and they'll separate themselves if we give it enough time.
Yeah. Yeah.
And that's how we do it?
That's
That's
how
how
we
we
do it.
separate
Yeah.
the thing that has 3 more neutrons than the thing that has 3 less?
Yes.
So they're...
That's how it works.
I mean, what is a mass of a neutron? Not a lot.
One Dalton or whatever it is, you know.
Whatever unit we've given to
Yeah,
it. Yeah.
I mean, that's why this, like, getting mad at Iran, because it's like, oh, they're firing up another cascade of centrifuges. You don't do it with one lump and separate it completely. You have a series of cascades.
Sure,
So you
yeah.
enrich
That
it.
makes sense.
You skim the really light stuff and then concentrate it quickly, and then you're left with all this depleted uranium. Why is it depleted? It's depleted from U-235. It's depleted of the lighter stuff.
Right. Because it was a mix when you put it,
It was
in
a
there.
mix, yeah.
When you mined it, was it a
Yeah,
mix?
yes.
Okay, so
And
you
it's
got
like
you have a chunk of metal, but each different atom in that chunk of metal has a different number of neutrons, conceivably. Not every unique.
It's homogeneous.
Not a unique number, but
Yeah, it's homogeneous. You know, if you have 100 atoms of uranium in your hand, your natural uranium ore, 99 of them are going to be uranium-238, and one of them is going to be a 235 somewhere in there.
I see.
If you have a big lump, those little tiny U-235s are homogeneously scattered.
Right, so you have to mine the good stuff from the stuff you've already mined, basically,
With the centrifuge.
which is
With a
or a
fucking
series of centrifuges.
Yeah. And they draw a lot
That's-
there's a reprocessing facility. France gets like 80% of its electricity from nuclear, and it's all the solid fueled reactors. And one of the biggest plants they have is devoted to enriching spent fuel that's already been through a reactor. And it takes like 3/4 of the power of this whole nuclear plant just to enrich, just to do that. It sucks a huge amount of electricity. Like, you could power a city or you could power a uranium enrichment facility, but not both.
Yeah.
Where do you get that energy from?
I feel like the language is. I don't like the enrichment. Didn't give me the right picture of what was actually happening.
Yeah.
You're separating.
You're
You're not adding anything to anything. You're just
Well,
Yeah.
you're
concentrating the-
sorting.
you're-
concentrated, yeah.
Yeah.
The right.
Yeah.
Concentrated.
Yeah. That
So
would-
yeah, just not distilling, but something
Kind of like-
closer to distilling than enriching.
Yeah.
For my money.
And honestly, if they had made a different language choice, we might very well call it distilled uranium.
Yeah.
You know,
Right.
Why not? You know?
Yeah.
Because enrichment is not necessarily a better adjective.
Yeah.
Anyway,
So you spend all this energy to enrich the uranium, and then you have to go through a very complicated process and turn it into a solid ceramic uranium-235 pellet, right? It's a lot more uranium-235, but it's still only like 30%. Still, the majority of it is 238, believe it or not. Uranium-235,
okay, so it's just a little denser.
it's a little denser.
than in nature.
Yeah.
Or significantly denser, but
Yeah, quite a bit.
But it's
relative
still-
to less than 1% to 35% is a lot.
right. Okay, 35%. Okay, yeah.
So uranium-235 is fissile. If you hit it with a neutron, it will almost always split every single time. Uranium-238 is not.
Mm-hmm.
That's why uranium-235s, which make a bomb out of, that sphere we saw, that picture, the uranium pit, that's heavily enriched in U-235.
Okay.
If you had the same amount of uranium-238 and had it together, you can't make a bomb out of it. Literally, you can't do it. If uranium-238 gets hit by a neutron, it absorbs it and turns into plutonium.
Wow.
We got into that, you know.
Yeah, we did.
So, a light water reactor,
Where does it get the proton from again?
the neutron?
No,
It
I
gets-
know, but to turn into plutonium,
Oh, okay. So it absorbs a neutron.
does it get bigger or smaller?
Bigger, and
Right.
then it spits out an electron. That's the beta decay.
Right.
The neutron turns into a proton.
Right, that's what it was. Yeah. Thank you for reminding
Yeah.
me. We did cover that.
Yeah, Mr. Creosote eating the
Yeah.
wafer. So after you've done all this work to get a ceramic pellet, you're ready to go.
Yeah.
You're ready to make some heat out of it, right?
Yeah.
And you put it in a fuel configuration, a fuel rod, and you lower it in. You go, hey, cool, we're grooving. We're
We're gonna
heat.
make some steam.
We're gonna make some heat. We're gonna make some steam. Why do we like steam? We spin it in a steam turbine.
I love
Why
that
the fuck do we do that? To spin a magnet. Why are we spinning a magnet? I don't know. It's cool. No, because if you spin a magnet and it's next to an electric wire, it goes woo.
Yeah.
and wiggles down that wire all the way to your blender in your kitchen.
I mean, back to the centrifuges being sort of hilariously mechanical and clunky. Like, I remember when I first learned that these sci-fi, most modern nuclear reactors were just
Steam.
steam engines.
Sure.
Yeah. That's
Right,
all
that
it
blew my mind. Like, whoa.
Well, you've seen the cooling plants.
Yeah.
You know, that's what they're doing. Is,
Right.
is. Yeah, they have to condense the water back down.
Yeah.
If there was a crack in the earth that just emitted perfect steam, okay, put a turbine over the top of it. Doesn't matter where you get your spinning from.
You're just spinning a generator or a dynamo or whatever they're called.
And it's nuts to think about, but you're sitting there, you spin your blender. Why is the blender spinning? Is it magic? No, it's because if you trace that goddamn wire all the way back somewhere, it's because there's another wiggly spinner at the other end. That's it. Mechanical motion
To mechanical
to
motion.
mechanical motion.
Mhm.
If it was air pressure, you would understand it.
But my toaster, it's mechanical motion to heat
Yes.
rather than mechanical motion.
Yes. Yeah. It's lovely to think about.
This is not very interesting, but I don't know if I've told you this before, but when we were living in the castle together, I had this sort of, steampunk inspired fantasy of a house like the castle that, rather than having electric appliances, had maybe a water powered humongous flywheel where all of your modern appliances would just, with mechanical transmission, hook up to this one central, 10-foot radius flywheel that's constantly turning, but slowly. But with the right transmission, you hook your blender in there and it's going bzzz.
So you'd have a little zzz on the wall, and then you would
exactly.
you'd have a clutch mechanism to fire up your blender.
Yeah, just a
This
dumb
is
little
an
fantasy
aside,
of
but
mine.
when you talked about the wire going from the blender to this, have you ever read Gravity's Rainbow by Thomas Pynchon?
No, I want to.
Read it.
Okay, yeah.
Read it. Yeah.
It's imagine if it was a Bronze Age or Iron Age or Renaissance person, and you're like, hey, when I need to boil water, I go into my kitchen and I push this lever down, and it does it. And the Bronze Age person is like, if I want to boil water, I have to go into the woods and pick up sticks and take them to my house.
Well, you could go back to my grandparents.
Yeah.
I mean, I was the first generation of my family to be born in a house. I was born in a house, not a hospital, I think, but I'm not sure.
Yeah.
I think it had running water and an inside toilet and electricity.
Yeah.
I mean, I'm the first generation. My parents didn't have it. I can remember an ice box. That's how old I am.
This is why,
I'm bad at cook. I was just thinking this recent. I'm bad at cooking with the knobs, and I got knobs with numbers on them.
Yeah, they tell you what it is.
Yeah, and I'm still bad at it.
Feeding
And then
sticks.
thinking of the
raising and lowering the
alternative,
pot.
like pre-natural,
Yeah. This is why in those ancient societies, this is why deforestation was the kiss of death. Once you're deforested, it's fucking over.
Yeah.
Your soil
That's
washes
all you
away.
have.
That's all you have. I want to smelt metal. I want to boil water so I don't die of dysentery. I want to make beer, or I want to make ceramics. Any of this.
And I kind of want to
to
cook
make it
my food.
digestible.
Yeah,
Yeah.
that's right, because my jaw doesn't work as well as it used
Yeah.
to.
Yes, it's there is a mountain in the city of Rome. There is a trash pile of olive oil pots that is like 200, 300 feet high because they were shipping olive oil and they couldn't recycle these amphorae clay pots, and so they broke them up and they piled them up in a big useless mountain. There is a mountain of clay pots in the center of the city of Rome from Roman times, the height of the empire. And all you have to do is look at that pile and say, how many trees were cut down to fire that much pottery
The kilns.
for a one-time use, so you could ship it across. You wonder why there's no trees in North Africa, because the oil came from North Africa. It was a tremendous. Where did they? They weren't burning coal. It was charcoal.
Yeah.
They fired those pots once. They filled them with olive oil. They shipped them north from Tunisia to Rome.
They got emptied.
They emptied it out, and then they broke it up. Brilliant. Great. What a way to use your wood. And we wonder why they collapsed.
Holy crap.
So
That's quite the legacy. It's not hard to.
I'll show you the picture. When
It's
we're done.
not.
really something.
It's not hard to see the family resemblance.
No, it ain't. The kiss of, okay, so if the kiss of death is deforestation before fossil fuels, what's the kiss of death? Peak oil, man. We talked about the metabolic requirements of civilization.
Mm-hmm.
So you make this ceramic fuel pellet and you put it inside of a nuclear reactor, and now it's generating tremendous amounts of heat because it's being bombarded by neutrons.
Do you have to do that yourself? You have to bombard it yourself, or?
Okay, so getting a reactor going is kind of like starting a fire. You have to have kind of kindling to get it going, but once it does get going, it's self-sustaining.
Okay.
Yeah. So a one uranium fuel pellet can't do anything on its own because it's too small. A chain reaction can't get going. But if you put a series of them together in long tubes in the right geometric
The fuel
configuration,
the fuel rods.
a fuel rod,
Wow.
it'll
Yeah.
get going and sustain itself. So,
Yeah.
so the uranium pellet, as you lower it in, nothing's happening, and now it's getting hit
Now it
by
can
neutrons.
talk to its
Now it can
neighbors.
talk to. Now it's interacting.
How
with its
far
neighbors.
away from? I mean, just the practical.
Well,
what are they in a hexagon? Are they in an
Yeah,
octagon? Or
kinda.
they?
They figured it out. They figured the geometry out very well, very precisely.
Wow.
So, what happens when nuclear fission is happening inside of a solid ceramic pellet? Heat
Well, it's
damage.
getting hot.
It's
Yeah.
getting hot. Uranium is splitting apart into other things. So now it was uranium. Now it's two atoms. That causes expansion and damage. One of the fission products eventually becomes a gas, xenon. You have a gas inside of a solid. It does tremendous damage to a solid object.
Well, it doesn't sound very safe when you
It's-
put it that way.
It's not. That's why they melt down.
Yeah.
And you have all these. You have a tremendous amount of like control.
It sounds like they have like an inevitable shelf life.
They sure do. After they've been in there about a year or 3, you have to take them out and rearrange them. You know, the ones that were farther away with less heat damage, you have to put to the center, and the center ones you have to pull out.
You
And
rotate the tires.
then rotate the tires. Yes, that's a good way to think about it. And guess how much of the energy stored by supernova inside of things like uranium or plutonium a light water reactor is able to use because of its solid fuel?
Not much, probably.
Less than 4%.
Yeah.
After that, it's so damaged by the heat and the neutrons and all that, they have to take it out, and they can never use that pellet again inside of our light water reactors.
Do they get to throw it through a re-enrichment process
They
or
can.
whatever?
That's reprocessing. That's what I
Right.
talked about with France.
But
That's
it's
the
it's
reprocessing
still
step.
it's tremendously energy expensive
Yes.
just to harvest
Right.
a little more
Yes.
of that 96% you've got left over.
Yes. Yes.
Oh,
And then
and there's going to be diminishing returns probably as you
There would-
continue to.
there would be a
well,
little bit.
it doesn't matter. Yeah,
but you're
as you pulverize it or whatever. So
yeah, I mean, if you're looking at a gallon of gasoline and you said, I can only use 4% of the energy in that gasoline, and the rest is going to be toxic waste for 100,000 years. Well, that's dumb.
Yeah.
A gallon of uranium light water reactor fuel pellets is that exact scenario.
Oh, so-
And I wish I was joking.
now you can
Yeah.
cook your chicken, but you only get. You light it once to cook your chicken, and you only get 4% of the potential chickens out of it.
Yes.
And then it's
And
either needs disposed of or reprocessed.
And even reprocessing, you get a little bit more, and then it's too damaged again.
And then,
Right, right.
Of course, the problem is, what do you do with what's left over?
What do you do with what's left over? There is 140,000 tons of spent nuclear fuel at 121 military sites and 104 nuclear power plants in the United States alone.
And nobody wants it in their backyard, right? They want the power.
Spent nuclear fuel, one of the interesting things about fission is natural uranium is still not very radioactive, U-238. It has like a 14 billion year half-life. Just like thorium, pretty much. Which means it's very low radioactivity.
It means it takes 14 billion years before the chunk of atoms you have has decayed into half the amount
Yes.
of atoms you
Yes.
you
Yeah.
started with.
Right. Right. So it's very slow. Decay, tick, tick, tick. Very radioactive stuff might have a half-life of 300 years. Tick, 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 tick. Very dangerous, but only for those 300 years, pretty much. You know.
And then
300,
it's not, then
600,
it's something else.
Yeah.
Well, I mean,
Yeah.
except for Zeno's paradox.
Right. Eventually, it does actually trail out where, like, you know, there are some vanishingly rare elements left over from that supernova, you know, that formed the Earth, the elements that formed the Earth.
I guess the last atom does eventually split.
It does.
It's not like Zeno's
And it
paradox.
does, right?
but, yeah.
It does, but some of the things they eventually decay into lead, and now it's just lead.
Right.
It was radioactive, but now it's just lead. Cool, not radioactive, right? The stuff in between is what's really dangerous. Just radioactive enough to be really nasty for living things, but long-lived enough, but not so radioactive that it decays quickly. You either want it to be billion-year half-life or as radioactive as you can possibly be, 20-year half-life, 11-day half-life. But 100,000 years or 200,000 years is radioactive enough to be dangerous, but not so much that it gets rid of itself. You know, it's very distressing because...
Dangerous to human civilization.
Yes,
Yeah.
and all life. Yeah,
Yeah.
you don't want to be anywhere near it. And boy, that spent nuclear fuel is exactly that, because it's just radioactive enough. It's still got a lot of uranium, but it's also got all these fission products and other really nasty things. And it's full of things called transuranics. It's a uranium that's absorbed a neutron but not split. Now it's more radioactive than it was before, but, you know, still not so radioactive that it's going to disappear. And this spent nuclear fuel is stored very often right next to an actively running light water reactor plant. And that's what those pools are, you see? Those deep pools with the blue glow, all those rods in them. Because they're still so radioactive, they're very hot. There's residual heat from inside the reactor, but they're also generating their own heat because they're still very radioactive. There's still 96% of the energy in there, right?
Yeah.
So at Fukushima or whatever, when there's disasters like that, if the electricity shuts off, the recirculation of that cooling water stops. It boils that cooling water away, and then you can have another meltdown just from the spent nuclear fuel. Not even the stuff in the core; it's outside the core, and often it's stored right next to a goddamn bomb inside of a pressure cooker because there's no long-term repository place for this stuff. We're just kicking the can down the road.
Yeah.
It's a radioactive, devastating can. And we're just kicking it. Just kicking it down the road.
Yeah.
And it's getting bigger and bigger because as long as these light water reactor plants are running, they have to put more fuel in there that they only use 4% of and then pile it up, just pile it up.
Yeah.
It's a catastrophe.
It's a catastrophe, yeah.
The molten salt reactor can't melt down because it's already molten. And it load follows with that electricity. And if you have a pound of uranium-238 that you've ground into a powder and dissolved into molten sodium chloride, you can use 100% of it because it just circulates around inside there until it gets hit by a neutron. And so the waste of a molten salt reactor is all of that really radioactive but short-lived stuff. 300-year half-life, 350-year half-life. I don't care relative to hundreds of thousands.
No.
It's much, much less.
Can you grind up these spent ceramic pellets and throw them in some molten salt?
Yes, you can.
Oh, great.
Believe it or not, the people who are really designing this, and it's so... I think we're witnessing something like a pre-Manhattan Project. There's a big online community, and it's really attracted a lot of really smart people and really devoted people. Jim Kennedy, John Kutch, Kirk Sorensen, Ed File.
These will all be household names in just a couple decades.
Let's hope.
Let's hope.
Yeah. And the ones who are looking at it, the guys who really understand it, they're like, again, like kindling, you can take this spent nuclear fuel and purify the stuff you can't have, but that's kind of trivial, like you can't just grind it up and just throw it in. You got to filter out a few of the nasty things. But you can take that spent nuclear fuel, and because it's radioactive enough and emitting all these neutrons and still splitting and stuff, you can use it as kindling to start a molten salt reactor. Because if you just take uranium-238 and throw it in there...
Could you even use it to melt your salt?
No.
Oh, okay.
You have to, the salt has to be molten first. And when it's molten, it's like 800 degrees Celsius, which is... The hotter the temperature is, the bigger your gradient between hot and cold, which means you can make much more efficient steam and spinning. It's just a natural part of the universe that the bigger the gradient between your heat source and your final end use, the more efficient it is at converting it into another form of energy. You can use that, I kind of got sidetracked there, that you can use that spent nuclear fuel as kindling to start a reactor, but once it's going, you don't have to use any more kindling. If I just had uranium-238 and I dissolved it into salt, it would not start a fission chain reaction because uranium-238 is not naturally fissile. Mm-hmm. But once fission starts in there, once I get the neutrons going, so I have eventually it'll be known. It's like if I have 3 tons of uranium-238, which is not naturally fissile, I need 800 pounds of spent nuclear fuel to start that reactor going. But you only have to do it once at the very beginning. It's like starting a stove. You need some tiny little twigs and, tinder to get it going. That's what starts it. But once the stove is hot and running, you don't have to add tinder anymore. You can put a big, fat, wet log in there.
Right,
and it'll take it. Yeah.
You could just throw some more uranium-238 in there when you need to.
Yeah.
There's...
so this community is mainly people in the United States that you're talking about, or
it's
international?
getting more. It's becoming international, but it did start in the U.S. and Canada. Actually, they've been having conferences for about 10 years. Yeah. The story, it kind of starts with Kirk Sorensen. He was a NASA rocket scientist who was given the arduous task of saying, how do you power a colony on the moon? Because there's 40 days of darkness, and so your solar panels don't work. And he found, I think literally in a book, like a physical book, the story of this molten salt reactor in Tennessee, and he was like, oh, that would work for the moon. And then he went, wait a minute. And so he got going, and he was kind of the spark, because he was giving presentations on his own in people's basements and things. I've watched a lot of hours of these guys.
But you're saying he's giving presentations in people's basements. Meanwhile, the $1 trillion project that got the whole thing going had to do with defense.
Yes. First.
Right?
Yeah.
And now he's trying to do something that's not for defense, and it's very hard to get a $1 trillion investment or $1 billion, right?
Yeah. Yeah, it is.
And not to mention the fact that when you were talking about sort of the well-defined, well-trod path of the nuclear engineer, I mean, that infrastructure not just being physical stuff, but even like this well-defined curriculum where I got an undergrad in physics, and then I'm eventually, going to do my whatevers, and then I'll know how to run this plant. Right.
Yes.
That doesn't exist yet.
There are no regulations for this because the regulations don't exist. And so when they come to a regulatory industry and they say, look at this new type of reactor we could do, that it's not a conceptual reactor. It was proven and run. Now there's a lot of different reactors on paper that are different flavors of the molten salt type. And the regulatory industry is like, and so what? You don't have the stamp from us. There's nothing to stamp. You can't come to them with a brand new reactor.
There's no scripture that even mentions it, so we don't have anything to refer to.
Yeah. And so they're stuck. They're stuck in this no man's land between an outdated light water reactor that should never have been used for electricity generation and this new reactor that there's no rules and regulations for, and you can't just go and say, I'd like to buy 5 pounds of plutonium, please. They can't even get their hands on thorium.
Yeah.
They can't do it. You can't go and buy thorium. It's classified as if it was uranium or plutonium.
You have
It's
to.
not.
We'll
But
have to
that's-
mine it ourselves.
But these are rules in the United States. How about places like China or
Ah, yes. That's why I sent out that email, because
Yeah.
China's really looking into this.
I remember the day. I don't think it was. Maybe that was the email. You found a reference to it on the English
He was pretty excited.
English version
I'm
of
still
the
excited, yeah.
Yeah.
People's Daily, or
Yeah.
yeah.
Yeah. So this reactor can use this type of reactor, especially this certain configuration, the sodium chloride fast spectrum. There's details about neutrons that matter. But basically what you want is the cheapest, safest, and most robust reactor that can take the most diversity of fuel and have the least amount of waste. I think those are 5 things that are worth considering, right? I don't care if you have some really cool, super fancy reactor that can do this one neat thing. I don't care about that at all.
Yeah.
I want a reactor that's the equivalent of a wood stove that you can just fucking put whatever you want in there and it's going to make heat.
Yeah.
Because energy poverty is poverty.
Yeah.
These poor parts of the world need electricity now. And they need it to be so cheap and abundant it's almost free. And there is that type of molten salt reactor out there. And it's actually, believe it or not, this online community I'm talking about has already been split into factions. There's the people who want this reactor, and this other guy has a patent on this other reactor, and it's successful when the infighting starts.
Yeah.
No, yeah.
Yeah.
They're all unified at the beginning because they're like, we just want a molten salt reactor. Now it's whose molten salt reactor, who's going to get the money, you know.
Yeah.
So that's actually a good sign. This type of reactor can use spent nuclear fuel that's been through a light water reactor system and use it as kindling and basically turn it into something harmless.
I was going to ask you that, is
Yes.
how much of it gets used in that kindling process, right? Because that's
It'll get
one
used
of the
up.
problems,
Yeah.
right?
Yeah, it is. And but that really robust reactor is fine with that.
That's great.
It uses up the kindling, and then the leftover,
And then we don't-
the ash from the kindling, so to speak, just floats around in the salt.
Yeah.
Whoop, whoop, ba-doo. Circling around. The design of it is so simple. For especially this robust one, all you need is a pump, a pipe, and a pot. The pot is where fission happens because it's the right shape geometrically. The pipe is what circulates the salt around through a heat exchanger, and the pump is what moves it. Because since it's liquid, it does that load following and the thermal expansion of reactivity, right?
You need to take that hot molten salt and put it near some water you want to boil.
Yes.
Basically.
Yeah.
Okay, that's the pipe.
Right. Yeah. The pipe includes your heat exchanger.
Right.
In the pipe, no fission is happening because you want it to be safe, even though conceivably, make your pipe really thick and safe for fission. I don't care. It doesn't matter.
Okay.
Because the salt is always going to be molten and circulating around. You just circulate it around and pull heat off, and so the reactivity matches the amount of heat you're pulling off. That's power generation.
The heat goes to the water that turns the turbine.
Spins a turbine. The turbine powers your civilization. There's no carbon dioxide emitted, and you have to put in a tiny trickle of uranium or plutonium powder, about 3 pounds a day, to counteract what you're doing, because you're turning matter into energy. It's 1,000,000 times more energy dense than burning coal.
Yeah.
Yeah. A big coal plant in England takes 9,000 tons of coal a day. A day, every 24 hours. 9,000 tons. In these huge trains, this big train where the train doesn't even slow down and it just lowers the coal through, down into chutes below it. And, it slowly goes. And then the coal is put on conveyor belts and pulverized into dust and then shot into these big boilers to boil it up. And it's like, oh, you could do that, or you could move 3 kilograms a day.
And the workers who maintain the facilities, if they ever deign to raise their eyes, they see the glowing eye of Sauron above them.
Yeah, yeah. And
Well,
that
that-
means 9,000 tons of coal ash a day, which is,
Yeah, and to go back in history, those coal miners were working in those seams, digging it out by picks, and their mortality rates. And
Oh, God.
I've even seen English mines in China, Yunnan province, where you go in there and it's cave mining.
Yeah.
They're not. It's not these open pits, and these
Yeah.
people were dying young and
yes,
paid nothing, and
it's horrible.
it would happen. I mean, that's to go further back in history.
Right. But, I mean, the scale of this, we talked yesterday about if you wanted to engineer the oceans or if you wanted to do these big engineering projects, which we must do in order to repair the damage we've done to the ecosystem, well, they're all going to be powered by coal or natural gas or oil
Yeah.
if you do them.
Yeah.
If that's your energy regime, which makes it a moot point. Like, okay,
It does. Yeah.
plant a bunch of trees, drive.
That's
millions
like
of-
making a Band-Aid out of blood or something.
Yeah, it's just immaterial if you're going to do it powered by fossil fuels,
Yeah.
because you can't match it. The scale, here's the damage you did. You're going to do more damage trying to repair it.
Yeah.
Because if you're going to sit there and there's a type of rock that can neutralize ocean pH very simply, to counteract ocean acidification. And you need to grind up and pulverize about 7 cubic kilometers of it a year, about a mountain a year, or a few more than that. Well, if you're doing all that mining and crushing for coal, powered by coal or oil, well, you also have to do the work of mining the coal.
Right.
Yeah, sure.
So you're pushing water uphill.
Yeah.
Push as much water as you want uphill. Spin that wheel as hard as you want. The more water you push uphill, the faster you have to spin the wheel.
Who was
Right.
the Greek guy that pushed the rock up the hill?
Sisyphus.
Sisyphus.
Yeah, yeah.
Myth of
Team
Sisyphus.
Sisyphus. Yeah. Except instead of that's the cycle of history.
Yeah.
Anacyclosis. But instead of the rock rolling down, the rock just gets heavier and heavier.
Sure. Yeah.
But this is what is meant by collapse. That's exactly what Jared Diamond was talking about. You push that rock and it gets heavier and heavier. And then Sisyphus goes, oh shit, my legs are giving out.
Yeah.
And then he gets crushed by the boulder, and the boulder just rolls down and down and crushes everything until it reaches that new point of where it can't get any lower.
Yeah.
7 billion people are supported up here above ecosystem limits
Yeah.
by fossil fuels.
Yeah.
So if the fossil fuels run out, you don't just have everybody say, well, now we'll be farmers again. You
Yeah.
can't support 7 billion people on the soil of this planet.
You can't.
You can only do it with fossil fuels.
Yeah.
But at the last minute, there's this Superman. The space shuttle is trying to leave Earth, right? But you didn't plan ahead. There's not enough fuel, and there's a big crowd of people below going, huh? The engines are sputtering out. The flame stops, and all of a sudden the space shuttle stalls out.
Yeah.
Well, gravity doesn't end. Time doesn't stop. You don't get to say, you know what year it is? It's 1999, and it's going to be 1999 forever. Sorry.
Yeah.
And then the shuttle crashes down. Well, what if somebody comes up who has this molten salt reactor that can suddenly power things? That's the real race. It's the only one that matters. Everything else ties into it. You can use this reactor, and what's really cool is this online community has been attracting goofball weirdos who are like, you can hook up this other chemical engine. If I have enough heat, you can hook up a chemical engine that can use CO2 from the atmosphere to make methanol, which is fuel.
Yeah.
Other chemicals. Desalination.
Yeah.
You can do desalination on a massive scale if you have these type of reactors.
Yeah.
You could make the desert bloom.
Yeah.
It ties into everything. It's the energy source.
Where do I get one?
So there's reason for optimism.
That's what I mean.
Yeah. But of course that takes the leaders thinking not for profit. But profit would have to be part of it. Economics, obviously.
It
But
is the economics.
yeah. I mean, they'd have to think that way. But can we get our leaders to think that way? That's the problem.
these reactors are so simple to operate, and the return on investment, so to speak, 3 kilograms a day being brought in to refuel
Yeah.
to power a city is so high that I believe a government could nationalize its energy system, make it completely national, not public at all. Like, you're a government employee and you have to do what we say, but you could make electricity free for your various stages of your economy. And I think the way to do it would be to start with heavy industry, steel smelting, iron smelting, ceramics, making paint, making paper, these other things. And then you move to secondary systems. You know, you make electricity free to run your buildings. Here's kind of a tidbit. For let's say a 5-story office building that has a 40-year lifespan, the cost of financing and building it and the labor and all that is only 30% of the cost of the building over time. 70% is heating, lighting, moving air.
Yeah.
You know, keeping the lights on.
Wow.
You make electricity there for those things free. And then the final stage is one where you say all citizens have free electricity forever, in perpetuity.
Yeah.
There's enough depleted uranium, which we talked about a while ago, sitting around in casks, heavily toxic, chemically toxic and radioactive, woohoo, to satisfy world energy demand for something like 5 to 10,000 years.
Wow.
Already above ground.
Yeah.
Already mined.
Already mined and already purified into uranium.
It's not depleted.
It's depleted uranium.
It's depleted.
Yeah. So you go to these casks. Here they are.
Do you have to enrich it to run your molten salt reactor?
Because you don't have to enrich it because you have that spent nuclear fuel as the kindling.
Yeah.
So you don't have to enrich it, even though it's even depleted. Because it'll sit there, you stick it in this reactor, it'll absorb a neutron, turn into plutonium, and then the plutonium gets hit by another neutron. It splits, and it releases like 3 neutrons. So 1 to be absorbed by the uranium, 1 to split the plutonium that came from the uranium, and then 1 more to just go out and keep it going. That's called your neutron economy.
Yeah.
And if it's above 2, you're looking real pretty.
Yeah.
It's really something.
Yeah.
But the 238 or whatever is not
Yeah.
fissile, right?
It's fertile. That's what it's called, being fertile. These are those casks.
That's a great word for it.
Yeah, it is.
Yeah.
It breeds. It's a breeding ratio.
Yeah.
So you
Or
put
so
the
it's splitting when it gets hit by a neutron?
the plutonium is. The uranium, depleted uranium 238, sucks in a neutron, gets hit by a neutron, and absorbs it.
And doesn't release any energy,
No, it doesn't.
even though it splits into plutonium?
No, it doesn't. It doesn't split into plutonium.
Oh, right. It just transforms.
Transforms. Yeah,
Yeah,
sure.
yeah.
It
An al-
breeds into plutonium.
Right.
Now the plutonium.
Right,
when
because
it
that
gets
neutron
it-
turns into a proton. Now I'm plutonium.
Yes, yeah.
Gotcha.
Yeah. So it's like, so Mr. Creosote's sitting there, big fat. Oh, I couldn't eat another bite. Oh, it's only wafer thin. Okay, so he eats that first wafer. He doesn't explode. He gets a little bit bigger. Whoop.
Well,
And then he goes, oh, I'm really full. Oh, I couldn't eat another bite. And now John Cleese goes, it's only one more. Mr. Creosote, okay. Oh. He eats that neutron. Now he splits.
right.
And he blows out over the room. He splits into 2 the fission products, but he also releases like 2 or 3 neutrons.
Yeah.
And as long as that ratio of neutrons, you're releasing a little more neutrons than you use, you have a breeding ratio, and you are making more fissile material than you are consuming.
Okay, hence the breeder.
Breeder reactor.
And fertile. I love that
fertile,
word
that's
for
right.
that. Yeah.
Fissile splits with 1 neutron. As soon as it gets hit by a
Gotcha.
neutron,
It's ready.
It's ready to go, and that's what you need for a bomb.
Or a light water reactor, apparently. Like,
Yes.
how come this doesn't happen in the light water reactors?
It actually does, believe it or not, because the majority of that ceramic fuel pellet for a solid fueled reactor is still uranium-238. Something
Right.
like a third of all the heat generated with all light water reactors, solid fueled reactors, comes from the breeding of the uranium-238.
To plutonium,
Plutonium
to then fission.
Yeah, yeah. They don't design it for it, but they can't do anything about
Gotcha.
it. If you put,
So this uranium 238, there's still all this energy.
tremendous. He's still
Ready.
Mr. Creosote. Yeah.
He just needs a little more coaxing to
He
be.
needs a little more coaxing. He needs 2 neutrons instead of 1.
I see. So really, it's just That's a nice way to think about it because I can count to 2.
Yes.
So uranium 238 needs 2 neutrons to give me some heat because it needs to turn into plutonium and then split.
And then split, yes.
It takes 2 collisions.
Yes.
Where the good stuff, the pure stuff.
Yeah.
The
kindling.
the coke to
Right.
coal or
Yes.
the
Yeah.
Colombian whatever.
The bam bam, yeah.
Yeah.
The kindling that gets your reactor
Just needs
going,
1 neutron.
Just needs 1. Yeah.
Okay, well that's a big difference.
Or if
twice as much.
Yeah, and some of it is radioactive enough, like uranium-235. It splits on its own. It doesn't even need to get hit by a neutron.
Because it's sitting around
It's
about ready to
it's about
burst,
ready to
depending
burst.
on its half-life.
Yes, and so the half-life of U-235 is like 700 million years. Million.
But you've
Uranium-238
got-
is billions of years, right?
Okay, you've got so a half-life is 700 million years, but in a pellet that you could hold in your hand is how many million atoms?
Yeah, I mean, yeah, it's
So
it's so many. Yeah.
so many. So depending on how
Well-
much you've got, you could hold it and be pretty sure one's about to decay.
Yes, yeah. I'll show you a
Just
video
based
of a
on
type
the
of
statistics.
Yeah,
and-
it's quite beautiful. It's
Yeah.
called a cloud chamber, where they put a little piece of uranium and they put alcohol vapor.
Yeah.
And it
Yeah.
causes ionization, so you can sit there and watch.
You can see him go boop.
Yeah.
Yeah, that's
Yeah.
cool.
It's really cool.
Yeah.
And it really, I think it's useful to watch those videos because it illustrates.
Oh,
Oh,
man.
this is a radioactive metal. Under normal light and conditions, it looks like a piece of iron.
Yeah.
But if you put it in a cloud, you go, oh, there's a lot going on.
I just watched that episode of Star Trek, The Next Generation. You remember this one?
No.
Okay, Data, the android.
Yeah.
He crashes on a planet that's like sort of medievally,
Oh.
maybe just pre-Renaissance. I don't,
Sure.
I could make a better guess, but I'm not going to try.
Yeah.
But he's lost his memory, and he's got a box that says radioactive. He doesn't know what it means, and he doesn't know who he is.
Oh.
And then there's this sort of like proto-scientist in the village who like talks very confidently about things being made up of 4 elements, but also has this like curious mind.
He's
and
an alchemist. He's an-
Experimental.
Yeah.
Well, the doctor was a woman, Adam.
Oh. I'm so sorry.
Anyway, but then Data, even though he doesn't remember who he is, he's got more of a refined sort of scientific method and
Oh.
experimentation, and he remembers things about how the universe is put together. Like he knows that wood doesn't contain these 4 elements and it smokes because of this and the
Yeah.
Anyway, there's a scene where people are getting sick because
Radioactivity.
they've got these radioactive rocks, right? And he first like invents a microscope, or he doesn't quite invent it, but anyway.
Yeah.
But then he has this screen, and he says, "Oh, I've put something on this screen," and like you can, he's postulating that this thing is emitting invisible particles.
Oh, yeah.
And then and he says, "Oh, and see when I put this box in between, it stops." And I can't remember what he said about what he put on the screen, but it made me wonder if that had an actual basis. I didn't realize.
Yeah.
I was like, that's probably a thing, but I'm not familiar with that thing.
Yeah.
So it's the same stuff in your cloud chamber.
Yeah. I mean, they were doing experiments with. There's a famous gold foil one where they were shooting. I think it was electrons through a 1 atom
I don't
thick
recall.
gold.
I remember
Foil,
something about that, but
It's not Dalton. It was somebody else. And they made the point that it's the equivalent of shooting a cannonball through tissue paper and having one bounce back at you. And that's kind of how they got to the idea of the nucleus, because electrons shouldn't do that or something like that.
Yeah.
The early atomic experiments are really neat. How they did it, how they calculated what one negative electric charge is. They were
right.
coating things in oil and
Yeah.
giving them a static
Yeah,
charge.
what is this
and
oil that allows you to see these the
the particle? It's just we could make one. You can make one in your house. You just
It's
have
not-
super saturated alcohol vapor in a chamber, They use them to
So-
find like cosmic particles.
So
It's really
as the
it depends. It could be an alpha particle. It could be an electron.
okay,
right?
so as it
zips through.
the fluid,
They could measure something
it's
that it all
running into the
It's bouncing into things and causing ionization, which causes condensation
Yeah.
of the ethanol.
okay,
Yeah, yeah.
okay.
It's beautiful.
Interesting.
It actually is. It's genuinely beautiful. It's really. I'll both see it later.
Okay.
But
Sorry, I went on a TNG
no,
tangent.
no. That's good.
Because in the show, it was like you could see it like little, they light up. It was like sparkling.
Sure.
But I didn't know if that was a real thing or
I
not.
don't know if that. I don't.
Could
think
you-
that's
Well, it
Could
has
you-
to be something you can measure.
Yeah.
I mean,
Well,
that's what it requires. It has to be changing light or changing.
Yeah.
Right,
something.
exactly.
Yeah,
Right,
yeah,
exactly.
It would have to be.
And I mean, when Marie Curie and them were working on radioactivity, they realized there was genuine. They were like, it's emitting too much heat for chemical energy to do this, and it's doing it too steadily. And it challenged thermodynamics at first because they did not have the
They
theory.
didn't know where the heat was coming from.
Yeah.
Wow.
Because they had the thermodynamics down, and it's like this isn't possible with our current understanding of chemicals.
This can't be a chemical
This
reaction.
can't be a chemical reaction.
Because the math doesn't add up.
Yeah.
Well, it's like Lord Kelvin's challenge to Darwin, which Darwin had to speed up evolution because of that. The Earth can't be that old for evolution to occur because it was all thermodynamics, no radioactivity. So radioactivity saved the age of the Earth.
Oh.
You understand? I mean,
Yeah.
that just not. Kelvin was arguing from purely thermodynamic point of view.
Okay.
With radioactivity, we now know the Earth can be old, and it is old.
Yeah.
Yeah.
Something like a third of the heat generated in the Earth's core comes from radioactive decay.
Yeah.
But because the Earth is so deep, it is so thick, the heat gets trapped inside. It's insulated. So it can't. Even though the radioactive decay is relatively slow from thorium and uranium and whatnot, it's not a runaway fission reaction. It's just decay of natural stuff, but the heat stays trapped inside because it's 5 kilometers down.
Where's the rest of the heat come from?
Some of it's residual heat
Right.
from the formation of the Earth itself a long time ago.
Right.
Yeah.
But there's no reactor down there.
There's no reactor, but I think the neutron flux is a little bit higher, so I think the background reactivity of fission is a little bit higher than it is on the surface.
Interesting.
Don't quote me on that. I've tried to look up before, like, what's the neutron flux at the Earth's core? Because neutrons are everything when we're talking about this.
Okay.
So,
Oh, it's just another thing. It's a good reminder. Like,
yeah.
it's a question up there. Like, why is the sky blue or whatever?
Yeah.
Why doesn't the moon?
Right.
But it's like, wait, I know that we have a molten
Cool.
molten core,
Yeah.
and it's hot. But why is it hot?
Why
Why
is
is
it
it
hot?
hot?
Yeah.
Yeah.
And
It's not generating
before
energy.
They discovered,
Well, except for the radioactivity.
It is,
But
yeah, before they discovered radioactivity, there was no other explanation except just thermal cooling.
Yeah.
That was Kelvin's argument.
right.
But I mean, you
I
talk-
see.
That the Earth would have frozen a long
It would have
time
cooled.
ago.
Yeah.
It would have cooled down already.
Yeah, it couldn't be as old as Darwin was hoping.
I see.
And so he introduced some Lamarckian ideas to speed up natural selection.
Oh.
Seriously.
Similar with the uranium, the two concentrations. So 235 is less than 1%, but it only has a 700 million year half-life. That means 700 million years ago there was twice as much,
Yeah.
and then with twice as much. So go backwards, and eventually you get to the point where there's enough uranium-235 in natural uranium ore in the ground to sustain a fission chain reaction. And they went, yeah, if you go back about 2 billion years, there should have been enough for if there was a really rich seam of uranium, natural uranium. It's 2 billion years ago. There's no land animals 2 billion years ago. There's no multicellular life 2 billion years ago. There should have been natural uranium reactors, natural runaway fission reactions, and eventually they found one evidence of one in Africa, somewhere, Cameroon or something.
Oh, be darned.
And what happened was this is going back to the fast and slow neutrons. Water would seep down, groundwater would go down into this uranium ore, and it would slow the neutrons down, which makes them more reactive for uranium-235. And it would start a runaway fission reaction, just like a light water reactor. But then the heat would build up that it would boil off the water and shut it down. And it ran for like millions of years. The water would go down, heat
Get
up,
boiled off.
boil off, and then penetrate down again. And when they looked at this uranium ore that came fresh out of the ground, they were like, this stuff with its isotopes and its fission products and leftovers looks like it's been through a reactor. That's impossible.
Whoa.
That's
It
how they
was.
did it.
Yeah.
Yeah. And it had been, but it was natural. It was
Yeah.
just nature made
Yeah.
it. That's the only one they found. There's a lot of uranium in Central Africa. There's some of the richest deposits are there.
Yeah. It's amazing. Science is amazing.
Yeah.
I mean, it really is.
So here you go. So now that we're going to have this molten salt reactor, you keep hydroelectric until the molten chloride breeders reactors are in place. You eat up the food chain with molten salt breeder reactors. The first ones that you replace are the light water reactors, and you use the existing waste there to you shut down the solid fueled reactor. You plug in place your brand spanking new molten salt reactor, and you use the existing waste on site, you purify it, and you start it up, because all the safety regulations are in place, and all the workers there already understand electricity. You don't fire them. You're going to keep your job until you're dead, and they already have the steam turbines, and they already have all the electricity generating there, right? You don't need to do new infrastructure, just replace the energy source. Coal next. Yeah, the coal people don't understand radioactivity, but you're not going to lose your job. We're going to guarantee your job. You're going to keep the same wages. Your new supervisors are going to be people trained in this reactor, but we're going to retrain those of you who you want. Those of you who don't want to, that's fine, whatever. The economy is growing now because electricity is cheap. The price of consumer products is getting lower and lower because the cost of smelting your steel or mining your rock or all that other stuff is dropping to zero because you've made the energy source zero. Then natural gas. You divert the natural gas to chemical feedstock. Once you've stabilized and ramped up these systems, then you start replacing the hydroelectric dams so you can restore your natural flow of your rivers. There's no steam turbines at the hydro plant, but you could figure that out. Put a steam turbine in, because all the electricity generation is still there, right? The magnets and the,
Sure. Yeah, makes sense.
transformer stations. And then you can convert eventually to even more efficient spinners, more efficient dynamos than steam. You can use supercritical carbon dioxide and others that are more efficient at converting heat into motion. And there's a 1
But
million.
you're still using turbines.
It's
Still a water wheel.
Well, until the day comes we have magic ways to spin our blender. You got to spin it. You could do it by hand.
Yeah.
But you're not going to do that, are you? Electricity is just too damn useful.
You can't just turn heat into electricity.
I mean, in this room, you
yeah.
have electricity becoming heat. You have electricity becoming light. You have electricity as energy storage. And if my blender was running, it would be electricity turning into spinning.
Right. No, I just think it's funny that the only way we can harvest the heat is by spinning. In the beginning.
Yeah. Well, and the other thing is, it's so hot you can actually use it for other chemical stuff. It's really interesting. It doesn't. You can even go beyond that. Like desalination isn't spinning.
Right.
It's other. It's just kind of
You can use
passive.
the other ways directly.
Yeah.
Huh.
And there's 1,600,000 tons of depleted uranium that could power our current energy needs for 5,000 to 10,000 years. And then you would have to go, well, now we need to go mine some more uranium.
Yeah.
Do we have a decent idea about how much to expect left? Like how much have we mined of the Earth's supply of uranium?
I don't know. It's kind of immaterial. Uranium's easy to find because it's radioactive. When they look for uranium ore deposits, they do it by airplane, and I'm not joking, because they just have a Geiger counter.
Yeah.
Tick, 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 tick.
That's like, I mean, I don't
It's
know.
insane.
I don't know if I mentioned this dude to you. I think I've told you about him before. He was like an Eagle Scout. He was a kid who tried to build a breeder reactor in his backyard. He ended up getting into all sorts of trouble, and
I would hope.
he didn't. His life didn't end well,
Oh,
actually. No. But I mean, he would drive around. He put a Geiger counter on his car. He would drive around to past towns with antique stores and stuff. And one of his best finds was, because he used to harvest the paint that they used to put on clock faces to make them glow in the dark. One of his best finds, I mean, he was just looking for these clock faces
Yeah.
to begin with, but he actually found a clock in one of these antique stores where the last person who serviced it or who built it left a bottle of the paint
Oh my God.
for when it wore off
boy.
to
Oh my gosh.
to repaint the faces, right?
Wow.
So that was one of his big caches that he
Damn.
discovered.
Well,
But he would drive around with a Geiger counter on
Yeah.
his car to find
Yeah.
whatever it was he was looking for.
Yeah. The other thing is, we haven't talked much about thorium. We don't really hardly use thorium. It's more abundant than uranium, and it can be used in these reactors just fine.
Yeah.
It's more abundant than uranium, and it's as easy to find, and there's less isotopic diversity with thorium. So you can basically take thorium, that's thorium oxide or whatever it is, in the ground, dig it up, crush it up, refine it chemically, and you don't have to enrich it, unlike uranium.
Right.
Yeah.
So there's a thorium is almost as abundant as lead, and so this conversation of are we going to run out of uranium? No, and that's not even including thorium.
Does it have the same or comparable energy
Yes, yeah, it does.
baked into it, I guess?
Yeah, basically anything that's going to be fissioning of those heavier elements releases so much energy that the relative difference between them is real but kind of immaterial for us.
Gotcha.
For our purposes.
And as long as if we're just thinking 500 years ahead, that's fine with me. It doesn't have to be
Yeah,
more
wouldn't
than-
that be nice?
Yeah.
Yeah,
I mean, really.
it's extraordinary.
Yeah.
You could
Rather than 3 months.
Yeah.
Yeah,
Or,
quarterly.
yeah. The next election or the
Yeah.
or the quarterly report
Yeah.
for the businessmen. Yeah.
That's
if
right.
you look at Wall Street or Washington D.C., they're kind of like a pirate haven. They just kind of sit there and swoop around the world and plunder whatever they can. So of course they're only worried about the next 3 months. Their way of seeing the world, if you really dig into it, and what really motivates them, their main motivation is fear of getting caught. They have the attitude of criminals
Yeah.
because they are internationally.
Yeah.
You know, it's just crazy when you think about it. Like, here's a central government that's supposedly, and the whole America and Western civilization, because of its colonialism, is a pirate nation.
It is a pirate. Yeah.
And the arrow, the phrase is the arrow has broken against its target. Russia and China aren't putting up with this anymore, and we cannot plunder them.
Yeah.
These pirates are always terrified of strong central governments
Yeah.
because they're like, we're just here to steal from the weak. That's it. So America's not going to develop this reactor. Good. We're not going to do it. We don't care. We're like, yeah, whatever. We're here to bomb people in Yemen. We're here.
Or at least sell bombs to people who will
Yeah.
bomb people in
Yeah.
Yemen. One or the other.
Right. We have a monopoly on Saudi Arabia's oil, and that's really all that matters. And so whoever does this molten salt reactor is going to make an end run around not just the United States, all of fossil fuels and all of Western civilization. They'll make an end run around it.
Yeah.
We don't need your oil. Imagine if China was powering its car fleet with ethanol and made from methanol, made from these molten salt reactor plants. We don't need oil. And think of how much CO2 they're scrubbing just passively.
Yeah.
You scrub out 1 million tons a day, but you also burn it the next day into your liquid fuels
Yeah.
as a liquid fuel. Okay, cool.
Yeah.
Liquid chemical fuels like gasoline aren't going anywhere. They're too convenient. But if you have a clean source of them where it just doesn't matter, okay,
Yeah.
whatever.
Yeah.
That's your balance. That's neutral. That's carbon neutral right there. And then maybe 1 out of 10 or 1 out of 15 of these reactors that they're building are devoted just to scrubbing
You're
CO2.
saying people might get to keep their internal combustion engines?
Yeah, of course they won't.
The renters still get the wrench? That's so exciting.
Isn't it possible that batteries could develop where that energy could be stored in
No,
batteries?
we could get into the details.
No,
Yeah.
just yes or no.
It's a no.
Yeah.
Batteries are extremely useful for some uses,
Yeah.
and they're not good for transportation.
Yeah.
They have to do too much at once for cars.
And they're too heavy if they...
Too heavy.
Yeah.
And and they need too much material. They're actually very good for
Flashlights.
flashlights. But they're really batteries are because it's low.
You get different flashlights and batteries than I do.
They're really good for batteries. Are really good for tractors for low speed, high torque
torque.
conditions.
Yeah,
I don't
okay,
know
yeah,
why.
Yeah. Yeah.
But apparently, like the idea of an electric tractor is actually good, but an electric car that's high speed, low torque, lots of starting and stopping.
Well, a tractor would be heavier, need more traction. I mean,
Oh,
that
sure.
might be related to that.
I think so. Yeah.
Yeah.
It's just a physics. It's just
Yeah,
a physics
yeah,
thing.
sure.
And all of these problems are kind of physics until you run into the psychology of like, why don't we do this?
Yeah.
It's pretty clear why. Do you think the Pentagon is ever going to be anything other than what it is? Something that kills poor people?
Yeah.
Our military has no offensive capacity anymore. It's all flank and no front.
Yeah.
If we were to try to do anything offensively, you'd have to gather all your highly trained military forces from all over the world.
Yeah.
They have nothing to do except sit there and get shot at.
Or you could talk about your $1 trillion airplane too. What's it?
$1.5 trillion.
What?
Yeah. So the other half is renewables won't work.
Yeah.
Wind and solar can't do it. They can't. It's a system that can gather energy but has no fuel.
Yeah.
And it fries out your electric grid. We could get into this. This is a whole other talk.
Yeah. Let's not.
Wind and solar can't do it though.
Yeah.
It has to be a molten salt reactor.
Yeah. I think we should stop.
Okay.
Is that all right?
I was just thinking about the Pentagon. I was-